Thank you very much, Nick, and thank you everybody for being there, and thanks a lot for the invitation. So I'm going to talk about some of my research, but we do algebra and also applications of algebraic geometry. It's not going to take you to very deep formulas, but I want to give you a taste of what is the mathematics can come together and which areas are involved to the current research in computer graphics. So I hope you can see my screen, right? So this story begins when people were modeling chips. And this was done, well, this was way before the computers appeared. So you needed to have something, wooden piece of wood, so that you can draw somehow what was going to be the model of the chip, and put some things that people call DAGs, which are the ones here. And these kind of things were kind of resembling what was the weight that you wanted to put in some particular parts of the chip that afterwards you wanted to construct. This kind of structure is what nowadays we don't use it anymore, but this is where the word splines come from. This was used for many years in order to construct not only chips, but also afterwards to construct the cars. And then the idea was, okay, so what can we do this in a more organized way, and what are the things which are coming from mathematics can help us to build this in an organized way, and in order to also to be able to share information also with other people that are constructing the same object. At the same time, there were some problems solving differential equations, and particularly problems in elasticity. And so some people were working at the same time. One of them was Courant, and he was the first one who proposed to actually subdivide the domain if you want to have, you want to construct some mathematical model, and if you want to approximate a surface or a volume. He was the first one who suggested, well, maybe we don't need to use a complicated mathematical structure, but we can perhaps subdivide the domain and use discretization in order to approach those problems. So this happens in the 40s, when he proposed this idea. And I have here also on the right, this is Sienkiewicz. The thing is that this idea, at the beginning, Courant when Courant proposed this idea, you can imagine that if you want to subdivide something, you cannot do it by hand. You will need a computer in order to compute all the little parts and to do all the little approximations if you want to construct something big. So it took many years to actually people in engineering took those ideas and put them into function. And this was in the 60s, 70s, and that is why Sienkiewicz became very important. And he was based in Swansea, and that is why I have here him there. All right, so here we have the first idea that Courant proposed. So it was to subdivide the domain in using triangles, and to use that thing in order to construct functions which were going to approximate the surface. So I have here a model of that. So this little subdivision that you see in the screen, it only has these 6 triangles. But you can imagine if you want to construct something more complicated, let's say you want to construct a car, then what you need is to somehow try to model this and try to approximate a surface using some sort of thing like this, correct? So you will have little triangles that they are going to approximate a surface. They might not be perfect, but this is an approximation or a first approximation that you can make. Of course, it's going to be easier if you do it in the computer, but you can imagine you can model something like this by using just flat pieces and little ones if you want to approximate something complicated. This is what is called current element, and this is still now used for solving a partial differential equation in equations, which is a method called the final element method, which started with current. Then you can imagine that maybe you want something which is not just flat pieces, but you want to increase the smoothness and to increase how this surface look like. And if you do that, then you might consider having a triangulation which has more triangles, but in such a way that the curve is smoother, that you consider something on higher degree. I will explain in a second what it is, but something like that. So these other people proposed this, and this is these were other people that they were working in similar problems, but now they were working in car companies, and they wanted to have models for the cars, which they were able to save and also to share and also to produce cars in a more efficient way. So these people were working not in final element methods and not solving differential equations, but they were working in modeling, and they also came with a similar idea. So the one I have on the left, he is Bézier. He was an engineer working in Renault, and this is a kind of car that he was able to design. Or help to design. And then we have the Casteljo. He was a mathematician working in the company, which was the competition of Renault at the time. And this is a car that the people wanted to have somehow, that it was smooth, and that you can have such a construction to do such a car, okay? So they came with an idea, not together, but they were competitors, but they came with a similar idea that nowadays we just put all the things together. And these are the kind of things, or the kind of curves that they are using the computers to produce the letters that we use in PostScript, and also in well, this is in PostScript, in Type Roman, and also in Mac or in some other computers. Okay, so these are the kind of things that they propose, and these are the ones which are used still nowadays. This kind of subdivision and this kind of approximation was used not only for cars, but it was used for constructing or for modeling airplanes, particularly after the Second World War. And then these are also the construction of the kind of things that they use to have the animated movies. The functions, the mathematical functions that they use are a little different. They are called subdivision surfaces, but the idea is the same, is to have something which is simpler. So you take a bigger picture, you subdivide it, and then in these little parts you work something which is simpler than just taking all the things at the same time. These sort of ideas are used also in architecture. So this is an example. This was an exhibition in Paris, and this is made with triangles, and they use a hybrid structure where they not only use flat pieces, triangles, but they also use quadrilaterals because well, you can imagine that constructing something which is not completely flat is not that easy. So what it seems to be working is the combination of, in this particular exhibition, was the combination with triangles and quadrilaterals. All right, so this is the kind of functions I'm talking about. So this is a Bézier function, it's an example. So here we have some pieces. So there are two different ways to construct the Bézier function. It's called Bézier because of Pierre Bézier, who was working in Renault and came with this idea. And the algorithm that nowadays we use to construct those functions is the Castelló algorithm. So here we have, this works by interpolation. So here we have a convex combinations. The DAGs are nowadays replaced by something which we call the control points. And these are given by these pieces here. So first you construct a line going through those 2 points. If you have 3 points, then you construct 2 lines and you consider a convex combination of the 2 lines. And then you get something like this. So first you have the 2 lines. If you take the convex combination, you get this curve. And if you work further and you take a convex combination of these 2 curves, then you get something more complicated, which is of degree 3. It's a polynomial that you can see here. It's still a polynomial. It depends on 4 parameters of 4 control points, and are the ones which are used nowadays to construct these letters that we see in the computer. This is also the basis for the Adobe Illustrator and other drawing programs nowadays. This was generalized to 2 dimensions. So now you don't have only curves, or you don't have only lines or pieces of little curves, but you can also do surfaces. The one I have on the left that is moving is a combination of Bezier curves, but do you take nerves, it's called, so it's a rational function. This is used nowadays to do the modeling or the design in the CAD companies, the computer-aided design companies. And you would like also to have, or what it leads you is to consider or to ask yourself which kind of domains you can use. The ones I have here are just some of them. So for example, you can think, what happens if I have such a subdivision? Can I construct a surface on it? Or are there restrictions in the partition that I take on the plane and then to construct the curve or to construct the surface? Sorry, what are the conditions that I can get, and are they different? I'm free to consider any kind of surface, and which is the kind of smoothness that I can get. Do I get something very rigid as the current element, or can I consider something, what is the degree that I need in order to construct something very smooth that you see in the movies, for example. And at the same time, is this model good so that I can perform analysis? Can I solve differential equations with that partition and this kind of subdivision? So those are some questions that they are not completely solved nowadays. These are some of the subdivisions that we consider. This is playing around with combinatorics and with the mathematical structure that this has. I have taste here of this kind of a structure. So again, so here I have just some subdivisions in the plane. Here I have some subdivisions in 3D. You can also consider polynomials defined on these kind of partitions in 3D. And then you will have, or you will be able to model volumes, which is actually what people would like to do nowadays, because it will generalize curves, surfaces, and then if you get more volumes, it will be great, right? But it's very difficult, and it's still open to do such thing. So what happens in algebra is this. So you will have, for example, this kind of partition, or the one you have for Quran or whatever. You have a partition, and what happens is that in each of the little pieces, you want to have a polynomial. Each of these, so this is a polynomial, the f, the g is another polynomial, and you want that those 2 polynomials, when they meet along an edge, you want some smoothness, so you want the function to be continuous, but also you want to take derivatives, and you want the derivative still to be continuous until some degree. So you want to be able to take several derivatives, and still you want to be have something which is smooth. And then your picture will look very nice. So this is the kind of relations that happen here. So the relation leads, so this relation of saying that the pair of polynomials are CR continuous across the edge is in algebra, what it says is that you need this difference of the two polynomials to lie in some sort of ideal. An ideal just means that this difference of the polynomials is a multiple of another two polynomials, in particular of a line which is vanishing here on the edge, right? So this is the kind of relation that happens. This relation is quite nice if you look at it from the algebraic point of view, because it leads a lot of relations with other areas of mathematics. For instance, when you consider a line, which is the one defining the edge, instead of considering that equation, you can consider just the coefficients of the line, and you go immediately to something that is called the projective space. So this leads to study those lines and to construct those functions, which looks very nice or very smooth, instead of considering that bunch of functions or those bunch of edges that you have in the partition. You can consider all the points. This defines some ideas which are very important in algebraic geometry, and they are called 5 points ideals. And what it means is that instead of considering all the bunch of, so this is an edge now, and you can imagine you have several tetrahedra glue around this edge. In each tetrahedra, you have some polynomial. And the thing is that each of those planes which are meeting in that edge, they lead to just one point in projective space. So this is how the picture will look like. And instead of looking at the splines, you can jump and look at some points instead of looking at complicated lines. And this has a lot of connections with other things in mathematics. You can see here, for instance, this line is a secant, and this connection between the splines and secant varieties and those kind of things in algebraic geometry. So particularly, I told you there are a lot of open problems in this. You can imagine it depends on the combinatorics of the partition. It depends on the algebraic properties of the polynomials, and also you have some analysis going on related to the smoothness of the little pieces. So in particular, if you go to construct splines on volumes, there is a lot of research on this in algebraic geometry related to fat points and secant varieties, and there are problems that they have been open since the 70s, and related to secant varieties. But here, for instance, the way to look at this is, and this is some recent work with a colleague, that instead of looking at these complicated splines, which are defined on these volumes, you can look at the combinatorics of these objects. The combinatorics means how many planes you had in the original, for example, if you look at this thing here, we have a octahedron. We have 3 planes which are meeting in the middle point, right? Those 3 planes are the ones I have here. They correspond to these points, these 3 points, and the configuration is quite simple. It changes a little if you just move the point a little bit. Just the combinatorics is just completely different. You get something like that, because now you need to count how many different planes are meeting in that point. And since you shifted, this is going to be different. And the other is for the bipyramid that I have here also. So there are some combinatorics. It's not so simple. You get different configurations depending on where you lie, or where is the geometry of the partition. But there are some results coming from algebraic geometry which actually give a light how to solve or how to construct splines for practical applications. These are just 2 open problems that I listed here. This is the dimension of trivariate splines. Those are those splines I'm telling you defined on volumes. And there are open problems related to fat points ideals in algebraic geometry, but also what is the connection of those with the open problems in splines, particularly for the dimension of these, and how to construct bases that can actually be implemented. This is another thing not connected to the splines on volumes, but this is about how to represent complex shapes. For example, something like this. If you have a cloud of points and you want to do or to construct something which approximate that, how to do that. And because at least for me, it wouldn't be so simple just to construct something starting from a partition in 2D and try to come up with something like that on the left, on the right. So these are other splines which are called geometrically continuous splines. Is another open problem, and these are all the things I wanted to show to you. You can have a look of the web page, and there are some articles and some references that might be interesting to you. That's all. Thanks.
Excellent. Thank you very, very much for that. That was very interesting. Are there any questions from anyone in the Q&A session? Okay, well, I have a mild, we'll call it a mild question. So if I understood that correctly, modeling surfaces are fairly robustly understood to an extent, but extending that to solids isn't overly robust, because I frequently get issues where I take a series of surfaces and I'm trying to convert that into a solid to model. And so for me, obviously there's this order of magnitude difference in terms of what you're trying to do with a surface or a solid, but how far away? It's a very open problem that's been, you said, been going on since the 70s, was it?
So actually, so there are problems since Quran started doing that. The thing is that I didn't mention those problems. They are actually in 2D. It's very interesting that if you will have any kind of triangulation and you would like to construct a surface such that it's smooth until the first derivative, and you want just to have polynomials of degree 3, actually there is no way that you can find directly, or that there is not like a formula that tells you, okay, that is what you need to do. Nobody knows, and this problem seems very easy, very simple, but it's still open to find out in general what will be a formula for the dimension, and obviously a way to find a basis for such a space in order to implement such a construction. So that is open, and it has been open since the 70s, when people from algebra took those problems or that construction from final element methods, and people in analysis and approximation theory. Some people in algebra look at those problems and they started connecting this to other open problems. So there is this other one that I mentioned in 3D, which is more about secant varieties and fat points. And this was, there is a conjecture from the 70s, but probably the problem was there before. The thing is that the conjecture is from the 70s and is still open in several instances.
Okay, excellent. Thank you. There's a couple of questions now come in. One says, apologies if this has been touched upon, but can you explain what the desirable properties of subdivisions are from the point of view of algebraic splines, i.e. should there be regular, symmetry, or genericity?
Usually people in algebraic geometry, they like everything to be very generic. And the problem we have with the splines when we try to translate what those some results from algebraic geometry is that actually the things that happens with the splines are certainly not generic. So the desirable properties of the subdivision, I personally would like to be able to construct a smooth surface on whatever subdivision I have. So that is, for me, from the algebraic point of view, I would like just to be free to consider anything and just to be able to to say, okay, you can construct polynomials of such and such degree, and then here you can implement it in this way, and you can just use it. You can just give some control points, and that's it. So that will be my my wish. So from the point of view of algebra, there is no such a property. So in terms of the subdivision, we would like to do it as general as possible.
Excellent. Okay, thank you. Another question. Do you imagine that a solution of the solid parameterization problem could lead to a revolution in computing representation of a solid object? And for example, could this have implications in 3D printing?
Yes. 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 I think, I mean, the thing is that in order to solve the problems that I somehow said in 3D, you need to be, if you solve it, that means that you actually solve of the problems which are open in 2D. Because there are still problems open in 2D, and there is no way that you can solve completely the problem in 3D without solving the others. Okay, because some restrictions or some things that you can do in 3D, they just, the other one becomes just a particular case. So you solve that, yeah, it will have a lot of implications, not only for the splines, not only for 3D, but also for algebraic geometry too, because then we could probably translate some of the things which are happening, and now we know in the splines, and probably we can translate it to algebraic geometry, and that will be very interesting in that area.
Excellent. Okay. Next question. How did you come to study this area? From algebraic geometry or from graphics, or from another direction?
From algebraic geometry. Yeah. I have been looking at this problem completely algebraically. I have some collaborators who work as applications or do engineering and software implementations. But me, I had been looking at this problem from the algebraic point of view.
Okay, excellent. I think there's two more questions in the Q&A, and I think we've got time for both of them. So one says, even though the finite element method can be applied to solve PDEs, as can the finite difference method, is there any way that the finite element method can be applied to integral differential equations or integral equations in practical aspects, such as the Plemmel formulae for aerofoils modeling?
I really don't know that answer. Sorry. Sorry, but we will need somebody who is expert in the finite element method using it, but I don't know the answer for that question, sorry.
Okay. So as I was reading it, I didn't understand it either, so. And the final question.
No, I mean, the thing is that I'm, yeah, so if you ask me, I'm very algebraic, and you can ask me about geometry, but unfortunately, I'm not.
Yeah. Excellent. Okay. And the final question for you then is, you mentioned how lines in RR squared correspond to points in PP squared, but in the subdivisions, you are not dealing with entire lines, but line segments. Is it possible to encode that in PP squared as well?
It doesn't really, so you actually work with entire lines. So the picture I put there, sorry, where I am. So the picture I put here is, yeah, there is a segment, but you work with the entire line. What is important actually when you write down the property of the splines is that they belong to certain ideal and the ideal is generated by a power of a linear form. So it doesn't matter if the linear form is just, if you are considering for a spline, you consider just a segment. It's actually what it counts is the entire line. So so that's it. I work with the entire line.
Excellent. Well, thank you very much for a very interesting and informative talk. If nothing else, next time I get confused at my computer or annoyed at my computer while it's doing something, I can at least appreciate that it's probably me doing something wrong and not defining the problem correctly. So thank you very much.
Thanks to you.